much for the invitation. My name is Péter Maróti, and I'm working at the University of Szeged, the medical physics department. And I have the task to deliver a talk about the biophysical applications of laser light sources. This is a very wide field, and I constructed the lecture into three details, in three parts. In the first part, I should like to talk about the basic properties of laser light. This is some sort of introduction, or brushing up your mind, which supposedly it was talked to you last time, yesterday. But it needs some rebrushing, mainly from the point of view of the ongoing project and talk. Next, I will devote some time, maybe half an hour time, about some applications of lasers in biophysics research. This will be considered a survey because the field is so wide that it is impossible to devote too much time for the individual projects. I decided to talk about a lot of things, but in a very, very small depth. So practically I will consider the surfaces of the biophysical applications. And then the third part of the talk, I will talk about one special property of the light, which will make a distinction, real distinction between the usual thermal sources and laser light, namely the coherence and the photostatistics of the light sources. Now let's see the first part, the principles of laser operations and major properties of laser radiation. And this is a short summary. I suppose that these are all well known to you, but I will just run it through. The absorption and spontaneous and stimulated emission of light, which are connected to the Einstein coefficients. The population inversion and the optical gain, these are also essential parts of the laser operations. Nice to meet you. Good morning. Oh, good morning. There are ladies here. I am a little bit illuminated. Yeah, that's excited a little bit. It was started on a rather damped level, and now I'm a little bit more excited to talk to you. The third one is the laser oscillator. It belongs to the principles of the operation. The laser can operate in continuous mode, CW mode, or in pulsed mode. There are nonlinear effects which make possible the frequency to be doubled, for example, or in general to modulate the cavity. This will make possible to make cool switch, focal cell, etc., etc. Then we can change the wavelength of the laser, right? So these are so-called tuning the lasers. And there are different laser types which can be classified as solid state, semiconductors, gas, and dye lasers. These are the general introduction and summary which should be known to everybody who enters the secret field of laser. I will not discuss it. I will consider it as practically known to you. The next question is what are the basic properties? This is also a summary. The laser light is usually monochromatic. It has high spatial and time coherence, and it has small divergence and high intensity. These are the basic properties which usually you consider as these are the basic properties of the laser compared to the, I will just call it the thermal light sources, light bulbs. The next question, which I will answer in the third part of the talk, consider the basic question. What is unique in the laser light? How can we make distinction between thermal and laser sources? Of course, this is not a secret, but the coherence and the photostatistics are the major properties of the laser light. The next question will be how to utilize this high coherence of laser light. The second one how can the coherence and the photon statistics described in these electromagnetic fields, and how can it be used for practical purposes in cases where the photons, the number of photons are important, namely in the case of photon counters, where you can count the number of photons, 1, 2, 3, 4, etc., etc. Some processes will be also mentioned, of course, just on the surface to touch, namely the blackening of photographic layers, which is perhaps this physical effect is already unknown for the new generation. They do not know what is, so the hell is it, blackening of photographic layers, but these were very essential steps in the development of lasers and the whole physics, how the photographic layers are blackened due to illumination. And I will consider my major topics, my favorite topics, of photosynthesis, how the photosynthesis can utilize this photon counter nature of the photosynthetic apparatus, how the laser light and the thermal light sources can have different effects, considering say the productivity of green plants. If I should like to use Greek and bombastic words as phrases. Now, okay, so just these are the other steps. Just to again rebrush your mind about the two states, physics, how the absorption, spontaneous and induced emission can be derived, how the Einstein coefficients can be derived from the Planck's expression, and how these Einstein coefficients are related, how the Heisenberg relationship determines the delta E, this is practically the broadening of the light, the energy broadening, which determines also the delta nu, this is the frequency uncertainty of the radiation. Here you can see that there are differences between induced and spontaneous emission. This is practically the real background of all this apparatus which we are using here. There are two major differences between the spontaneous and induced emission. Nice to meet you. Take a seat. The next question will be also from the basics of physics, how the direction, diffraction will limit the divergence and the convergence of the laser light. And let's consider here a laser intensity profile, which should be for the first approximation can be considered as a Gaussian type curve. And if you consider here the E over 37% point on the foot of this curve, then you can determine this diameter or radius of the laser beam, which can be divided in near field or far field. In a near field is more or less parallel. Good morning, sir.
Good morning. Sorry.
And a good night?
Yes.
Quiet night. Long night. Okay. Could have been relaxed after this heavy dinner, no? Is it heavy? Not too heavy.
Very big.
Good. Depends on. Now we can summarize the basic properties. This is mainly due to the collection of the people who are to intent of the lecture. So nothing serious and important was announced yet. So you didn't miss anything. I'm afraid that at the end of the lecture you will also hear this type of expression, you miss nothing. I hope not so, but I was discussing here when you arrived about direct diffraction and divergence, diffraction limited divergence and convergence of the laser beam. First, here you can see about the directionality for a low gain system, for example using the Faraday resonator, the parallel feedback mirrors. This imposes some directionality, and this directionality is limited by the diffraction, and the angle of beam of divergence in this low gain system can be approximated by lambda over pi times RO, where lambda is the wavelength and RO is considering the radius of the beam. If you, on the contrary, you have a high gain system, then this divergence will be much larger than this limiting angle of beam divergency. Here you can see here took two examples just to get acquainted with this type of calculations. How can it be handled and what does it mean actually? In the other case, when we focus the beam by a length of f number, say 2, this means that the focal length is twice the lens diameter, then you will get a converging beam, but it will not collect it at a single point, as you can also imagine, because it is limited by the diffraction. And the smallest spot size can be approximated by this formula, and this d value is also sometimes called as the beam base. So this is the smallest diameter, but not of course not the point which will be collected. Okay. This was too much. The next property is the intensity of the laser light. Here you can see, this is a very classical figure I adapted from Janowski in 204. How during the years the intensity of the laser light increased. At the very beginning and the early of the 60s, where there was no possibility for any mode locking or cool switching, the intensity of the laser light was a couple of watts over a centimeter quadrat. In the 60s appeared the cool switching and mode locking, which increased the laser intensity tremendously. We reached practically with the chirp pulse amplification, practically we reached the energy of the bond electrons, so a couple of electrons range, and then a huge development occurred, which can be attributed to laser in the field of the relativistic optics. This threshold value was 10 to 31 watt over centimeter quadrat. These intensity is large enough to approximate excavate electrons relativity velocities, and very interesting phenomena can occur. The next border or limit can be seen here, 29. Above this laser, nonlinear effects will occur. Practically means that the interfering laser lights will interact with each other. They will not just living and meeting each other without any saying goodbye or anything, but they have a really large interaction energy, and they can modify their way of penetration. I can see, but that will be too far away. No? Maybe. Okay. High energy, power intensity, and brightness. That's a usual thing. I just mentioned here a couple of examples. How can it be calculated? For example, in the case of comparing the brightness of the sun with typical helium or gas laser. Okay. With a simple light source, light bulb, which has, say, roughly 20 watts, 5 meter distance on the retina, we have 10 watt over meter quadrat intensity, which is not too large, so we can look at the light bulb without any danger. But if we do the same thing with the laser light of power 2 milliwatt, of course it's a light power, then due to the high parallelism, the intensity will be much larger, so it's not recommended to look directly to the laser light, which is very well known thing. Okay, so this was just the introduction, and now let's see how the laser light can be applied in different fields of biophysics. I stress that this is an overview, and with not much demonstration, just text. First, possibility to use the lasers in different devices. This is the spectrometers or fluorimeters. The laser can be used in the visible or UV spectral range, or in the infrared spectral range. In the UV or visible spectroscopy, absorption, fluorescence, anisotropy spectrum, biomolecular spectra, whole burning, these are the selected topics. In the infrared and laser Raman spectroscopy, the field is much wider. The applications are much larger. For example, the spectrum can be taken in a Fourier transform form directly, not mathematical construction, but a physical construction. This is called FTIR spectrometers. We heard about already during this lecture. We will also have a lecture about a series of lectures, a separate lecture about the optical coherence tomography, which utilizes echoes of infrared light waves backscattered from the internal microstructures. We can use the lasers in attenuated total reflection mode, the ETR mode, which is a new and very efficient method in infrared spectroscopy. We can use the scanning microscopy also in the IR microscopy, and the Raman spectroscopy, which is a complementary method of the infrared spectroscopy, has also a very wide field of application. Actually, the effect was discovered by Raman by a very strong xenon light. This has a historical importance, but nowadays you can hardly find a Raman spectrometer with built-in xenon lamp. All spectrometers use laser lights, strong, very intense laser lights, and the comparison of IR and Raman spectrograms or spectrum can give you a wealth of information, because they are complementary methods. So some vibrations can be excited by IR, some not. And in other cases, if you consider the Raman spectrum, then some vibrations are appearing as a very strong Raman line, others are dead or appear practically as no spectral line. The next excuse me, maybe by, oh, that's another one. So the time resolved spectrometers, the bacterial chlorophyll fluorimeter I will mention, which we are doing actually in our lab, but not much details will be mentioned here because of the very speciality of this field. We can also determine the lifetime of the fluorescences or delayed fluorescences with different techniques, phase modulation or photon counting. And in the life sciences, in the field of femto and picosecond range, new biology arose, and mainly due to the, I would just call it the big bang of the biophysics, because the light absorption of the big bangs will give you a very well-defined start of the physical processes, and this big bang is practically triggering of the processes. For example, the photosynthetic charge separation, or electron transfer measurements, or for example, how the ligands around the center in the protein will be formed, etc., etc. Separate, a distinct field is a femtosecond coherent spectroscopy, different measurements of coherent protein oscillation and vibration, population decay, which is practically cooling, can be connected. Another field, a large field, of application of lasers is to reveal the structure of dynamics of biophysical systems. In this area, the main question is how the dynamics of proteins, DNA, biomembrane, etc., does determine the physiology of the molecules. So how is it related to the physiological function? Here you can practically consider the laser temperature jump method, the transient grating spectroscopy, which we are doing also in our lab, and then the fluorescence correlation spectroscopy. These are very, very special but very interesting fields. For example, the fluorescence correlation spectroscopy will illuminate a very, very tiny amount of the volume in the system, 10 to minus 15 liter, and this focused laser light, tightly focused laser beam will excite fluorescence, and this volume contains a very finite number of molecules which are able to fluorescence, and due to this heavy dynamics which is in this very small volume occurs, a large relative change in the fluorescence can be measured, which can be observed as fluctuation in the fluorescence. So this fluctuation is very different from the normal noise which you measure in the fluorescence, and if you detect this intensity fluctuations, then you can, for example, deduce different essential parameters. For example, how the fluorescence quantum yield of the molecule will change, or more essentially, what is the movement, what is the diffusion which controls the in and out movement of the molecules in this very tiny volume of the sample. The laser flash photolysis is also a separate area where the lasers can be used. The dyes can be photo-bleached by lasers. This photo-bleaching can be reversible or irreversible. In the case of irreversible photo-bleaching, a separate method arose during the years. This is called a FRAP, the fluorescence recovery after photo-bleaching. And from this type of microscopic measurements, you can use, for example, the diffusion coefficients of the different molecules in the system. How the principle of the operation instrumentation is realized is just a couple of keywords are mentioned here. In E. coli can be made such kind of measurements using green fluorescence protein. This is a very nice artificial protein which has inherent fluorescence. You don't have to take external fluorescence labels into the system. And the kinetic analysis of the recoverable trace will show you how the diffusion in slow and fast processes will occur, how the crowding effect will be realized, etc. The flow cytometry, cell separation is also another field. I will not go into details. The important point of this method is that quantitative separation and characterization of different heterogeneous cell suspension can be studied. For example, heterogeneous cell means that, for example, different types of cells, for example, cancerous cells or healthy cells are mixed in a system, and you can be able, using this flow cytometry, to separate the two types of cells, the cancerous cells from the healthy cells. I don't have to stress the importance of this method. The laser tweezer. This is another unique application of the lasers in the field of biophysics. Here on the first couple of slides will describe you what is actually this optical trap is, what the laser tweezer does. It has a lot of physics, and it can be very nice demonstrated what does it do and how does it do. Important thing that microscopic object, for example a single cell, can be lifted and can be fixed without causing any damage in the cell, and can be placed from one side to the other side. So it can be picked up by the focused laser beam. The forces which is arising in the system is due to the gradient in the illumination. So if you have a tight focusing, then the focal point the gradient of the illumination is very large, and this gradient will cause a momentum force. Using this force, you can pick up this molecule and can be fixed or can be put in another place. How can it be used? This very interesting phenomena. It can be these tweezers can be combined with other photonics methods, for example, spectroscopy. It can be fabricated different systems due to two-photon polymerization. Micro-sized objects with different shapes, propeller, etc. It can be constructed, and optically driven micropumps can be constructed. For example, the blood circulation can be, in the future time, can be used very effectively. And another application is, for example, making elementary mechanical studies, investigation in the field. For example, if you take a double-stranded DNA and you can fix one point with a laser tweezer with a gold sphere, then you can use this double strand, you can measure the tone, for example, this DNA. Was the problem? Okay. So with these methods, single molecule spectroscopy can be carried out, and also mechanical studies, which I told you. So not an average of the molecules can be studied by spectrophotometric methods, but also single molecule can be separated and investigated. Not also optical, but also not only optical, but also mechanically. You can construct force, elongation, or momentum torsion characteristic of a single elastic molecules, and this is a very, very large application in the field of elasticity of skeletal, cytoskeletal filaments, in motor proteins, or those proteins which are moving, rotating, for example, ATPs, etc., etc. Or not speaking about the muscle, which inherently makes a contraction, and this mechanical contraction can be also studied by single molecule mechanical spectroscopy. The mass spectrometry is also a very large field of application of lasers, mainly due to the field because you need an ionized molecule, because the deviation is due to the mass to charge ratio of the ionized state. So practically you have to bring the molecule, which, for example, the molecular mass should be determined or separated, should be put in the ionized state, and this ionization can be easily done by using lasers. For example, different methods are available. One favorite method is the MALDI, so the multi-matrix-assisted laser desorption ionization, etc., etc. So in mass spectroscopy. Lasers in medicine, don't have to talk too much because separate lectures will be devoted to the school in this field. It can be used in diagnostics and therapy, photodynamic therapy, blue light therapy, in surgical applications, photoacoustics. I think that yesterday you heard about it, not necessarily in medical applications, but in other fields of the photoacoustics. Reshaping of the cornea, this is a favorite topic here in Szeged in the physics department. Remote sensing, and this is the last one, which I collected. Laser spectroscopy can be used in light detection ranging. This is also the LIDAR system, which has in the last couple of decades enormous applications, and one of the good applications well known in the population is well known to the GPS. The masers, these were the ancient lasers. So the first is microwave amplified simulation emission of radiation was done in microwave range in the late 40s, and then with light it was done in the beginning of the 60s. And of course these have also potential biomedical applications. So this was just a short summary of the possibilities of lasers in biophysics. I collected this type of area because I delivered a course, usual regular course, and practically these topics, the frame of these courses Of course, here I do not have even a chance to get the further glimpse into these fields. I selected, these are just an overview survey or a glimpse of the very, very wide field of applications in the lasers in the biophysics research. The third part of the lecture is deliberately chosen one of the properties of the lasers, and I should like to concentrate on these single properties, and this is the coherence. Usually not much is heard about introductory courses about the coherence, but this is a very, very essential part of the laser, and also to understand the laser operation. This is why I devote the remaining time of my lecture, which would be half an hour time. I think so. So then the last part will be devoted to basics and applications. If I should like to make a very boulevard-like style to make an introduction and to stress the importance of this field, I constructed two columns. In the left-hand columns you will see a couple of thermal light sources. On the right-hand side some lasers. And the properties which we consider here, the directionality, small spot size, high energy, monochromaticity, coherence, photon distribution, these are all the possible properties, and the question is, which I should like to pose in this lecture, which properties are the essential properties? We will see soon that the directionality, although I stressed and described in the beginning of this lecture pretty much in detail, the directionality is not the essential property, because even the sunshine can be very well parallelized, and the divergence is comparable to that of the laser. I'm not speaking about some laser light sources, for example the diode laser, not very much parallelized. So this property is surely not a unique property of the laser light. Small spot size, tight focusing is also not, because the sunlight can be also very nicely focused. One of the first experiences who get acquainted with physics, how can it be, for example, burned or put to fire a piece of paper by sunshine for the converging lens. So this is surely not a unique property of the lasers. The high energy power, we saw that the laser could have tremendously light energy, but also the sunlight energy could be pretty light, especially if you focus it. So this is also can be highly considered as this is a property which is unique to laser light. The monochromaticity is also not, because if you have a good monochromatic system, or even a tungsten filament where you can make a very nice monochromatic beam. And there are a couple of lasers which we call it laser, but very far from the monochromaticity. For example, in this school you will consider the attosecond physics. I think that you heard a lecture yesterday. This is also laser, attosecond laser, but it's far from monochromaticity in this time range, although we consider this light source as laser. So this is also the coherence. No, that's a little bit, we are closer to it, but we will see soon. And it is also not a unique property, because even the light source, which is pretty far away, for example the sun, with a small angle of observation, it will have a large spatial coherence. So this can be also not very much considered as a unique property of the laser light. Remains in this list the photon distribution, and this will our task to study, because this will make a real distinction between thermal light source and laser light sources. So we will concentrate on the photon distribution. So again, to make another pretty much trivial figure, I took the picture from Friedrich Wilhelm Herschel, who discovered in the spectrum of the sun the infrared portion, where the thermometers showed increasing temperature, indicating although you do not see by your eye the infrared part of the spectrum, but still is present. So if you compare this figure to the formulate the question, if you have a darkened room, as Marshall had, Herschel had, and also on a small spot on the wall of the room comes a light source of unknown origin. It can be also a thermal light source, for example, the sun, or can be a light source from laser. Can you make distinction in the darkened room, sitting in the darkened room, then how to decide whether these two light sources were different origin or the same origin? Or this was a thermal light source, or this was a laser light source. So how to decide from inside whether it is a laser or thermal light source? It has also practical applications. For example, if you have a bone which should be healed by laser or light therapy, then the question arises whether this healing effect can be achieved only by laser light or by thermal light sources. So which property, if any, of the laser light is essential in this case? So let's get some introduction in the coherence. We can talk about, as you surely know, about temporal coherence and spatial coherence. How to determine the temporal coherence? The temporal coherence is mainly determined, or a classical way, is the Michelson interferometer, where the moving mirror can be displaced a little bit, and then the interference pattern or the fringes can be changed from sharp fringes to no fringes. And this is a classical arrangement how the temporal coherence can be measured. And practically it comes out that the temporal coherence, the time of temporal coherence, is inversely proportional to the spectral bandwidth of the light source. I do not want to go into further details. How to measure the spatial coherence? So don't forget, who do not have too much background in this field, the coherence means that you have stationary fringes or interference patterns. Stationary, this means that it will not change from one nanosecond to other nanosecond, but is continuously there. This means a coherence. You have a constant, not time varying interference pattern or sharp fringes in the pattern. Now the spatial coherence, a classical demonstration, of course, with a modern physics, it can be already shown another demonstration of the spatial coherence, but the classical one is a so-called Young's double-slit interferometer. We have two pinholes here separated in distance d. We have here a light source. At the two position of the light source, we have two on the screen. We will observe two interference patterns. One in the black corresponds to this position, the red one corresponds to that one. In both cases, we have a very stationary interference pattern, and they can be dislocated, removed, also displaced from each other. The question is whether this type of very strict fringes will appear always or not. So this distance practically characterizes the spatial coherence. I should like to stress immediately here that if we have a star which has a sun, has a thermal light source, and this star is very distant from us, so the light is practically has either a wave or a plane waves and enters to this Young's double-slit interferometer. It has an extremely high spatial coherence. So you will see here very strict sharp fringes or interference patterns, although I stress again and again that the star light is far from monochromatic. It is not monochromatic light, it is white light, and still has a very high spatial coherence. So the temporal coherence and the spatial coherence shouldn't be mixed with each other. They are two different things. if you are not very much persuaded that this is the case, so the stars can have a high spatial coherence, I usually use another type of example to illuminate the high spatial coherence of the light, or the thermal light source. You surely had an umbrella in a rainy day, rainy night, returning home, and if you consider, or if you look at the pretty far away standing street light, and between your eye and the street light, you put the umbrella. The umbrella has a very, very thin tissue. This can be considered as, in an optical sense, as heater. This is a German word. Grating, actually. It comes sometimes in German, and I can't escape it. So, so this grids, this very, very, very thin tissue exposes a grid, and at the other side of the grid, this is particularly eye, you will see interference pattern. Have you ever observed such kind of effect? Your country never rains, not? Or you never walked in the night in the rain.
My umbrella is very dark.
No, not so dark, not so dark. It is, if you consider a very thin tissue and you will put towards the street light. So this is, maybe it's not a common experience, but at the age that I had, you know, you made some long walking in the night, before, after, definitely events. And then it's unavoidable to look through the umbrella, the wet umbrella, and a far standing street light. And then you will see some rainbow-like structure. Never observed? So the rainbow is not quite another thing, because the Pride was organized in Budapest, if you do not know about that, recently. Rainbow, you know what's the rainbow? Don't miss it. Is it? So you will see rainbow, not in the street of Budapest. We are very proud of that, very proud. But in this lecture, we are proud to see a rainbow on the thin tissue of the umbrella in the night. Never experienced it. Okay, so the two pens, but you do not have two pens in the night. Umbrella, just the umbrella, a little bit keeping, and then put between the light source and your eye. And that's it. So all the necessary equipment for an experiment is available for you. On your left arm, a beautiful girl. And then, oh, excuse me, not girl, it could be also your friend. No, so that is correct. I'm very correct now. Yeah? So, but to keep the umbrella, you will experience this type of observation. Now, here you can also calculate what is the lateral coherence, especially result of the spatial coherence. You can also calculate, and here you can see this example which are overstressed for this example. For example, if you have a star, and this is the radian, this is the 0.01 radian, you can see the two, this is the light source, the street light. These are the 2 points, the extreme points of the street light, or this can be also a star, whatever you wish. And this is the viewing angle, this is denoted by alpha. And then, depending on the lambda, you will see the lateral coherence. In the case of, for example, the sun, this distance can be 50 micrometer. So 50 micrometer, this is the 2 pinholes are separated 50 micrometer, which is not a very short distance. So 1 micrometer is the diameter of a normal cell, bacteria. So 50 micrometer, if you list it in a double slit Young's interferometer, the distance, the 2 holes, beam holes are located in this distance, then you will see a very nice interference pattern. It's very, very strong fringes.